In the year 2009, a team of 3 scientists published the exact scientific recipe for a dust bowl. This was not a theory or a hypothesis, but a peer-reviewed and model-validated formula confirming causation. It detailed the specific ocean temperatures, land conditions, and feedback loops that, when combined, gave rise to the very disaster that claimed 7,000 American lives, decimated 100 million acres of farmland, and famously turned the midday sky black during the 1930s. Now, in April of 2026, every single variable from that formula has once again aligned over the southern plains. The drought has entered its 6th year, the ocean temperatures are a match, and the infrastructure designed to protect the soil has been quietly dismantled. This raises a profound question. Why is the federal government so completely silent? The answer may be more unsettling than the storms themselves. We invite you to follow our work on Calm Space as this story continues to develop, because we will be here to analyze every new storm, every new piece of data, and every change in the drought. The story of this unfolding crisis can be marked from March 15th, 2026, when the sky above Lubbock, Texas, took on the color of a dying star. This is not a poetic turn of phrase. It is a literal description. A wall of particulate matter descended that was so dense, the instruments built to measure air quality were simply overwhelmed, unable to process what they were sensing. The EPA's air quality index has a functional maximum of 500. A number that signifies conditions so dangerous that every national health agency deems them hazardous, advising residents to stay indoors, seal their windows, and avoid breathing outside air at all costs. On that day, Lubbock registered a reading of 1,400. The instruments were not broken. The conditions had simply entered a range the scale was never designed to describe, because its creators never imagined it would be necessary. This wasn't merely a data point. It was a clear and ominous warning. During that same week, the National Weather Service office in Amarillo issued what it termed a haboob warning. If that word is not immediately familiar, there is a good reason for it. A haboob is a kind of intense dust storm typically associated with desert landscapes like the Sahara, the Arabian Peninsula, or the Australian interior. Forecasters use this term when the outflow from a collapsing thunderstorm drives a towering wall of desert dust across an arid surface, with winds powerful enough to push cars off the road. It is a word that was never meant to appear in a weather forecast for the Texas Panhandle. And yet, there it was, in an official government bulletin from federal meteorologists who had evidently concluded that the standard vocabulary of American weather was no longer adequate to describe what they were witnessing. One of the storms from that period, for by this point, they were arriving in sequence, triggered a multi-vehicle pileup on a major highway as visibility plunged to nearly zero. This was not simply reduced visibility. It was an almost total blackout, the kind where a driver cannot see the vehicle ahead until the moment of impact. At the same time, anyone viewing NASA's Earth Observatory imagery from that week would have seen something deeply alarming. Plumes of dust, clearly visible from orbit, were drifting eastward across the continent. Their source was a region centered on the southern high plains of Texas and Oklahoma, the very same geography that had given birth to the devastating storms of 1935. The view from space confirmed the scale of the crisis unfolding on the ground. Here is where the situation shifts from merely dramatic to something genuinely strange. Every single condition observed in the spring of 2026, the duration of the drought, the exposure of the soil, the patterns of ocean temperature, the atmospheric circulation, and the failure of soil conservation programs was described in scientific literature years ago. They were identified as the specific, recognizable ingredients for a dust bowl, not just a drought or a bad season for dust, but the cataclysmic event itself. The researchers who unraveled this code published their work in the Proceedings of the National Academy of Sciences, back in 2009, a full 16 years ago. The science is not new, and neither is the warning. This brings us to the central question that this entire story revolves around, and it is worth stating plainly. If Washington has possessed, for 16 years, the precise knowledge of what causes a dust bowl, not a rough estimate or a theory, but a peer-reviewed model validated against historical data, and if every single ingredient in that recipe is now present across the southern plains, why is no one in the federal government willing to say aloud what is happening to American soil? The true mystery here is not the climate or the dust, but the official response. To understand it, we must assemble the full picture, because the pieces are scattered across a dozen different agencies, datasets, and news cycles that rarely connect with one another. The story only becomes clear when all of these elements are seen at once. We will begin with the science, not the current conditions, but the breakthrough that gave us the key to understanding the present. Before 2009, even scientists did not fully grasp the mechanism behind the events of the 1930s. The Dust Bowl was a known disaster, but its engine was a mystery. And then, 3 researchers changed everything. Today, we face a drought that has persisted for 6 consecutive years across Texas and Oklahoma, already surpassing the length of the initial drought that preceded the infamous Black Sunday of the 1930s. We have ocean temperature patterns that match the documented trigger for the original Dust Bowl with a precision that should be deeply unsettling. We have soil conservation infrastructure that has been quietly and methodically weakened over the last 2 decades, removing the very buffers that were put in place after 1935, specifically to prevent a recurrence. And we now have dust storms so vast and powerful that they are being described with vocabulary borrowed from the Sahara Desert. The recipe has returned. Every ingredient is laid out. And somewhere, in a federal building, someone who understands what those ingredients mean when combined is making a choice not to speak. That is the mystery we are exploring. But first, we must understand the recipe itself. Because until you grasp what was truly discovered in 2009, the current conditions might seem like a string of bad luck. After you understand it, they begin to look like something else entirely. We now turn to part 2. The 2009 breakthrough that changed everything. For many decades after the great environmental disaster of the 1930s concluded, a debate lingered among scientists over its fundamental cause. This might appear puzzling, as the Dust Bowl was an event chronicled in exhaustive detail through photographs, personal testimonies, federal archives, soil analyses, and meteorological records dating back to the turn of the 20th century. The consequences of the event were never in question. What remained elusive was the precise scientific mechanism behind it. While everyone witnessed its devastating effects, no one could rigorously explain why it began when it did, why it reached such an extreme severity, and most importantly, whether such a catastrophe could ever happen again. 2 primary, competing theories held sway for much of the 20th century, centering on either drought or farming practices. One side argued that the Dust Bowl was fundamentally a climatic event, a uniquely severe and prolonged drought that unfolded over a region of intensive agriculture. The other side contended it was a land use crisis, a direct result of reckless plowing that had stripped the landscape of its native grasses, leaving the soil vulnerable to the wind. Both arguments were supported by undeniable evidence. The drought was exceptionally harsh and real, and the plowing had been widespread and transformative. Yet, neither explanation, when considered in isolation, could account for the sheer scale and persistence of the ecological collapse. If drought were the sole culprit, then why hadn't previous droughts of similar intensity in the same region triggered dust events of this magnitude? And if overplowing alone was to blame, why didn't other heavily farmed areas that were not experiencing severe drought also turn into dust bowls? The 2 theories seem to point back at each other in a circular logic. The drought explained the dry soil, and the farming explained the lack of vegetation to anchor it. But the specific interaction that amplified a regional drought into a decade-long disaster remained a scientific mystery. This long-standing puzzle began to unravel in 2009 when a pivotal paper was published in the Proceedings of the National Academy of Sciences by Benjamin Cook, Ron Miller, and Richard Seeger. At the time, Cook was with NASA's Goddard Institute for Space Studies, while Miller and Seeger were researchers at Columbia University's Lamont Doherty Earth Observatory. Their work fundamentally altered the scientific understanding of the Dust Bowl. Using a series of climate model simulations, they could finally isolate the influence of different factors on the disaster's severity. What their findings revealed was a nuanced answer that showed how both sides of the old debate were simultaneously correct, in part, and incomplete as a whole. Their method relied on running general circulation models, the same powerful computational tools used in modern weather forecasting and climate projection. By systematically adjusting the inputs, they could deconstruct the past. First, they simulated the 1930s using the actual sea surface temperature patterns of that era, but without factoring in the degradation of the land. Then, in a separate run, they reintroduced the effects of that land degradation. The contrast between these two scenarios was stark, and it cast a new light on each variable's unique contribution. The initial simulation, which only included sea surface temperatures, confirmed a crucial part of the story. The distinct pattern of the 1930s oceans, a cooler-than-average tropical Pacific, paired with a warmer-than-average North Atlantic, was enough to generate a significant drought across the Great Plains. Within the model, this demonstrated that the configuration of the oceans was indeed a powerful and direct driver of the dry conditions. The atmospheric physics behind this process is fairly straightforward. A cool, tropical Pacific Ocean alters the path of the jet stream, pushing the storm track farther north and creating a large zone of descending air over the southern plains. Sinking air naturally suppresses the formation of clouds and rain. The model captured this mechanism perfectly, but here is where the discovery became truly profound. The sea surface temperatures alone did not recreate the full, devastating intensity of the Dust Bowl. This version of the model produced a drought, but it was not the historic catastrophe. The simulated temperatures were off, the rainfall deficit was not deep enough, and the self-reinforcing feedback loop was absent. It was clear that a critical element was still missing from the equation. Cook, Miller, and Seeger knew precisely what that missing element was. When they incorporated widespread land degradation into the model, representing the large-scale removal of native grasses for agriculture, the simulation was transformed. Suddenly, the model began to reproduce the extreme temperatures that matched the historical record. The precipitation shortfall deepened to align with what was actually measured during the 1930s, and most importantly, the devastating feedback loop materialized. The simulation now showed how exposed soil released more heat, how dust aerosols in the air altered the atmosphere's energy balance, and how the atmosphere itself responded to the wounded land in a way that amplified and prolonged the drought, preventing any natural recovery. What their work had demonstrated was that the Dust Bowl was not merely a drought that occurred at an unfortunate time. It was a failure of a coupled system. A climatic force, the drought, was acting upon a land surface that had been stripped of its natural resilience, creating a destructive interaction that neither factor could have produced on its own. The dust was not just a consequence of the drought, it was an active agent in sustaining and deepening it. This was the key insight that had been missed for decades. In a related paper from 2008 Geophysical Research Letters, Cook had already started to quantify this effect, exploring the radiative forcing of dust. This is the process by which suspended particles in the atmosphere absorb and scatter solar radiation, which in turn alters surface temperatures and atmospheric stability. These changes then feed back into the weather systems that govern rainfall. In essence, once the dust was lifted into the air, it began to perform its own climate work, actively changing the very system that created it. The Dust Bowl, it turned out, had developed its own sinister mechanism to prevent recovery. The implications of this discovery, for us right now in April of 2026, are sobering. The Dust Bowl is not a closed chapter of history, nor was it the product of unique circumstances that can never be repeated. It is a reproducible state of the Earth system. A specific formula, a particular pattern of ocean temperatures, combined with widespread land surface degradation, is what generates a dust bowl. That is the equation. And if we can identify that equation from the past, we can also recognize when its variables are aligning in the present. We can watch the recipe for disaster come together in real time. This is precisely what we are now able to do, and it is exactly what appears to be happening again. The question, then, is not whether we understand the mechanism. We do. The question is what we are prepared to do, knowing that the mechanism is once again in motion. Part 3. The ocean configuration has reappeared. In this unfolding story, one number holds more significance than nearly any other: the Oceanic Niño Index. This index, meticulously maintained by the National Oceanic and Atmospheric Administration, serves as the primary gauge for monitoring the state of the tropical Pacific Ocean. It specifically tracks whether sea surface temperatures in the central and eastern equatorial Pacific are running warmer or cooler than the long-term average. A positive index value signals El Niño conditions, bringing a warmer tropical Pacific and typically wetter winters to the southern United States. Conversely, a negative value indicates La Niña, with a cooler ocean and drier winters in the same region. The magnitude of this deviation from the average reveals the strength of the atmospheric forcing. As the winter of 2025 to 2026 began, the Oceanic Niño Index registered approximately negative 0.55, a state classified as a weak La Niña. By the early spring of 2026, this figure had shifted towards plus 0.16, approaching what NOAA considers neutral territory. To a casual observer, this transition from a weak La Niña to a near-neutral state might seem like a positive development. After all, if La Niña is associated with drought, then a weakening La Niña should surely mean the drought is also easing. While this assumption is entirely reasonable, it is also dangerously incomplete. The true picture, as research reveals, is far more complex. The pivotal research by Cook, Miller, and Seeger uncovered that a sustained, powerful La Niña was not the primary trigger for the 1930s Dust Bowl. Instead, their work pointed to a very specific combination of oceanic conditions: a cool tropical Pacific paired with an unusually warm North Atlantic. It was this precise pairing, rather than La Niña acting alone, that atmospheric models connected to the severe drought patterns over the southern plains. This distinction becomes critically important in 2026 because the second half of that oceanic equation, the warm North Atlantic, is not weakening at all. By multiple metrics, it is currently at or near record-breaking levels of warmth, having been anomalously warm for a prolonged period. The mechanism by which a warm Atlantic reinforces drought in the central United States is separate from the Pacific's influence, yet it pushes conditions in the same direction. While a cooling Pacific shifts the jet stream northward and encourages sinking air over the plains, a warming Atlantic alters the temperature gradient that pulls moisture from the Gulf of Mexico northward into the continent. In certain configurations, an unusually warm Atlantic can effectively choke off this flow of Gulf moisture, starving the plain states of the rainfall they would otherwise receive. Together, the two ocean basins create a kind of atmospheric pincer. The Pacific pushes the storm track away, while the Atlantic simultaneously reduces the available moisture. This exact configuration, a cool or neutral Pacific and a warm Atlantic, is what the 2009 paper identified as the oceanic fingerprint of the Dust Bowl. This oceanic pattern, however, is not some rare, once-in-a-century event. A review of the instrumental record, which extends back to roughly 1880, shows that researchers have identified between 8 and 12 instances of similar pairings over the last 145 years. This suggests it occurs, on average, about once every 12 to 18 years. What is unusual is not the pattern itself, but its convergence with a land surface that has been simultaneously degraded. Herein lies the most critical insight from the Cook research. The ocean configuration creates the drought, but it does not, by itself, create a dust bowl. For that to happen, the drought must encounter compromised land. In years when the same oceanic pairing occurred, but the land was healthy or protected by cover crops, the result was drought, dry years, and agricultural stress. But the catastrophic, self-reinforcing feedback loop of sustained dust mobilization did not ignite. The ocean may set the table, but the condition of the land determines whether the meal becomes a disaster. This brings us to a question that scientists are actively debating, and it is worth considering honestly. The North Atlantic has been warming on a multi-decadal trend, a phenomenon most climate researchers attribute, at least in part, to the atmospheric accumulation of greenhouse gases. If this trend continues, and there is no compelling physical reason to expect its near-term reversal, does it mean this dangerous ocean configuration will become more persistent, more likely to occur, and more prone to locking in place once established? While we lack a definitive answer, we are faced with an unavoidable observation. The configuration is present now. It matches the documented trigger for the original Dust Bowl, and it is converging with drought conditions that have already persisted for 6 consecutive years. The ocean may have initiated this sequence, but it represents only half of the story. The other half lies directly beneath our feet, and it has been changing in ways few noticed until the dust began to move again. This brings our focus to the land itself and the primary tool for measuring its distress, the United States Drought Monitor. This weekly report is a collaborative effort by the National Drought Mitigation Center, NOAA, and the United States Department of Agriculture. It maps drought conditions using a 5-tier classification system, ranging from abnormally dry at the lowest end, through moderate, severe, extreme, and finally to exceptional, the most intense category, signifying conditions so severe they require multi-year recovery times even after normal precipitation returns. As of early April 2026, the Drought Monitor revealed that approximately 89% of Texas was experiencing some level of drought, with a vast portion in the severe to exceptional range. Oklahoma was even worse, with nearly the entire state approximately 99% under drought conditions. The most severely affected region in the entire country was centered on the exact same geography as the Dust Bowl's epicenter: the Texas Panhandle, southwestern Oklahoma, southeastern Colorado, and adjacent parts of Kansas and New Mexico. Yet, the most alarming statistic is not the percentage of land in drought, but its duration. The current drought across the southern high plains has now persisted for 6 consecutive years. To place that number in its historical context, consider Black Sunday, the drought that led to that single most catastrophic dust event in American history on April 14th, 1935, had been building for roughly 3 to 4 years. The drought we are witnessing now has already lasted longer than the initial phase of the 1930s drought. We have moved beyond the point where this can be described as a simple run of bad weather that might resolve with the changing seasons. This is something else entirely. A 6-year drought is a concept far more profound than 6 years of below-average rain, a deficit that a single wet season might erase. It represents a cumulative crisis, a compounding failure within the land itself. With each passing year, the soil moisture deficit deepens, vegetation withers, and groundwater tables fall. The very surface of the earth can form a crust, destroying the land's capacity to absorb rain and its ability to resist the wind. Understanding this process is vital, because the link between the duration of a drought and the vulnerability of the land is not a straight line. The relationship is exponential. The degradation unfolds in stages. In the first year of drought, perennial grasses enter a state of dormancy, waiting for the rain's return. Annual plants, however, may not germinate at all, and the topsoil begins to lose its moisture. By the second year, the hardy perennials start to thin out as their root systems weaken and the soil's structure begins to break down. After a third year, a significant die-off of vegetation is underway. The root channels that once guided water deep into the ground have collapsed. This allows the soil to develop a hard, sealed surface that causes rain to run off instead of soaking in, preventing the replenishment of the soil profile. By years 4, 5, and 6, the landscape is no longer just a healthy system enduring a drought. It has become a fundamentally degraded soil system. This distinction is critical, as it determines everything that follows when the wind begins to blow. The way this modern drought is expanding is also a cause for concern. Eastern Colorado, which had previously been spared the most extreme conditions concentrated in the Texas and Oklahoma panhandles, experienced a swift and severe decline in April 2026. In the span of about 1 week, the region's classification dropped by an entire drought category. Such a rapid deterioration is not merely a statistical shift in weather patterns, it signals a system in motion. The drought is actively growing its footprint, spreading at a pace that eerily mirrors the expansion documented in the historical records of the 1930s. Wildfire acts as another powerful accelerant, compounding the drought's impact on the soil. In just the first quarter of 2026, flames consumed over 1.1 million acres across the southern plains. In this context, fire is more than a catastrophe in its own right. It becomes a preparatory event for the mobilization of dust. The blaze strips away any remaining vegetation and incinerates the layer of organic litter that helps hold soil particles together. It can even alter soil chemistry, further weakening its structural integrity. And when the wind inevitably arrives, it finds a surface left utterly defenseless, a landscape with no moisture, no roots, and no cover. From this exposed ground, the dust begins to rise. Between the years 2020 and 2024, the agricultural sector in the drought-stricken region suffered losses estimated at $23.6 billion. While this is an enormous figure by any measure, its true significance lies beyond the economic data point. This number tells a story about the condition of the entire system. $23.6 billion in losses indicates that the agricultural infrastructure of the southern plains has been under sustained, years-long stress. It means that farmers have been forced to draw down their reserves, not just financial, but also the vital reserves of soil and groundwater, simply to continue their operations. The system is not in a state of balance, it is in a managed decline. The tools being used to manage this decline and prevent a more rapid collapse are themselves under immense strain, which brings us back to the heart of the matter. The configuration of the oceans initiated the drought conditions, and the drought has inflicted its damage upon the soil. Yet, whether these conditions culminate in a new dust bowl or merely a severe, prolonged drought hinges on one final variable: the state of the land itself. And in 2026, the condition of that land is far more precarious than many realize. To understand the present, we must look to the past. During the 1920s and early 1930s, an estimated 5.2 million acres of native shortgrass prairie were transformed into cropland. This was an ecosystem that had blanketed the high plains for millennia, with root systems that reached 6 to 8 feet into the earth. Its plant communities had evolved to survive drought by going dormant, not by dying. The ploughing of this sod was rapid and mechanized. Driven by the immense profits from high grain prices during World War I, at the time, the drought had not yet begun. The land appeared productive, and from a short-term economic view, there was every reason to plough. But that native sod was more than just vegetation. It was an integrated structural system. Its deep network of roots physically bound soil particles together. The organic matter in the root zone created aggregates, clumps of soil, that resist wind erosion because their mass and cohesion make them too heavy to be easily lifted. When you plough native sod, you shatter these aggregates, fragment the root networks, and expose the loose, individual soil particles that were once locked within a living matrix. You are not just removing plants, you are converting a stable surface into a potential source of dust. When drought arrives and the crops fail, all that remains is bare, unprotected soil on a flat, windy landscape, with nothing standing between it and the sky. That is the story of history. Now, consider the story of the present. The Conservation Reserve Program, or CRP, was created in 1985 as a direct policy response to this history. Its purpose was to take fragile, erosion-prone farmland out of active production and convert it back to vegetative cover, typically native grasses or other perennials. In structural terms, it was a partial reversal of the ploughing that occurred in the 1920s. While a native sod ecosystem cannot be fully restored on such short timescales, the program created a meaningful buffer against wind erosion on the most vulnerable lands. At its height, around 2007, the Conservation Reserve Program had approximately 36.8 million acres enrolled across the nation. By 2026, however, that enrollment had fallen by roughly 11 million acres from its peak. Let that number sink in. 11 million acres. To place this in perspective, the total area of native sod that was ploughed in the years leading up to the Dust Bowl was 5.2 million acres. The amount of protective cover that has been removed from the landscape through the decline of the CRP over the last 2 decades is more than double that historic figure. It is, of course, important to be precise. The decline in CRP enrollment is not a perfect, one-to-one parallel to the sod ploughing of the 1920s. The land leaving the program was not all located in the southern plains, nor was all of it on the most erosion-prone soil types. The situations are not identical, and yet the parallel is impossible to ignore. The fundamental direction of change, the large-scale removal of protective cover from vulnerable land, is the same. Land once shielded by protective vegetation is now returning to cultivation, a change driven by clear economic pressures. The Conservation Reserve Program, or CRP, offers federal payments to farmers for keeping land idle. However, the value of these rental rates has not kept pace with potential farming profits. When it becomes more lucrative to cultivate marginal land than to keep it enrolled in the CRP, farmers logically resume planting. This reflects not a moral failing, but a rational response to an economic framework that has been allowed to weaken, signaling that short-term production is valued over long-term protection. Another layer of this story involves the Great Shelter Belts. In response to the Dust Bowl, the Roosevelt administration initiated the Great Plains Shelter Belt, a series of windbreaks stretching from Canada to Texas. Their purpose was practical: to slow wind, capture soil, and retain moisture. Between 1935 and 1942, an estimated 220 million trees were planted. These were never intended as simple ornamentation. They were a form of living, functional infrastructure, designed to prevent history from repeating itself. The science of a shelter belt is simple. Trees create drag, slowing the wind and creating a protected, calmer zone downwind for a distance of 10 to 15 times their height, Slower wind has far less erosive power. The relationship is not linear. A 10% reduction in wind speed can cause a much greater drop in soil loss. Yet, since the 1990s, research has documented the widespread removal of these shelter belts. The reason echoes the decline of the CRP. Mechanization, modern. GPS-guided agriculture is most efficient on open fields, where trees are obstacles. Removing them boosts operational efficiency, but eliminates the very wind protection they provided. As organizations like the Environmental Working Group have shown, the protective systems built after the 1930s disaster are being systematically dismantled. The situation grows more concerning with the influence of federal crop insurance. This subsidized program shields farmers from losses, including from drought and wind erosion, a sensible safety net in an unpredictable industry. However, the incentive structure it creates warrants a closer look. A farmer can receive a CRP payment for keeping marginal land in grass, or they can plant it and receive an insurance payout if the crop fails. When market conditions make the potential insurance payment greater than the CRP rental, the rational choice is to risk planting on vulnerable land. This creates a paradox. The system financially rewards the land use practices that increase dust bowl risks, while underfunding the program designed to prevent them. So the pieces are now in place. We have ocean patterns conducive to drought, a prolonged 6-year dry period, and soil that is increasingly exposed and vulnerable. That second key ingredient, the widespread land degradation identified by 2009 research as the amplifier needed to turn drought into a dust bowl, is no longer a future possibility. It is a present reality. When these two elements converge, the result is not a simple sum of their effects. The system begins to power itself, creating a dangerous feedback loop. When we imagine the 1930s dust storms, we often see them as a symptom of the dust bowl, the visible result of drought and wind. While this view is not wrong, it is critically incomplete. It misses an insight that helps explain the duration of the original dust bowl and why similar conditions today could lead to another sustained catastrophe. Dust is not merely a passive byproduct. Once enough is lifted into the atmosphere, it transforms from a symptom into an active agent in the climate system, a feedback mechanism that does not just signal drought, but actively works to prolong it. The physics are fascinating. Dust aerosols in the air interact with sunlight in two ways. Fine particles scatter sunlight back to space, cooling the ground below. Coarser particles absorb sunlight, heating the atmospheric layer they occupy. The net result is less solar energy reaching the surface. While this might seem helpful, the atmospheric consequence is significant. A warmer mid-atmosphere above a cooler surface creates a stable atmospheric column. This stability suppresses convection, the vertical air movement needed to form rain clouds. Less convection means less rain, which deepens the drought. A deeper drought exposes more soil, which provides more dust for the wind. The feedback loop closes, with each cycle making conditions worse. This concept was scientifically grounded in a 2008 study by Cook in Geophysical Research Letters, which quantified the feedback for the 1930s Dust Bowl. The research showed that dust's radiative effects significantly contributed to the drought's persistence. The dust was not just a consequence of the dry weather, it was an amplifier. This reframes our understanding. The Dust Bowl was not simply a drought that produced dust. It was a drought that created a dust feedback that helped perpetuate the drought itself. In a very real sense, the catastrophe became self-sustaining. Just how powerful this feedback is remains a key uncertainty in the current science. Different climate models yield varying estimates for how much dust forcing contributed to the 1930s drought persistence. Calculating the precise impact of this effect is a complex challenge and continues to be an area of active research. We understand the mechanism of this feedback loop, but we are still working to measure the exact degree of its power. The finding that dust functions as a mechanism for sustaining drought, rather than merely being a neutral consequence of it, is a conclusion supported by multiple, independent lines of analysis. The implications of this for our current situation are sobering. The dust events observed in early 2026, the AQI of 400 inches, Lubbock, the widespread haboob warnings, and the vast plumes visible from space are not simply signs that conditions are poor. Instead, they are direct evidence that a powerful feedback mechanism is now in operation. Every major dust mobilization that achieves sustained continental transport is actively performing work on the atmosphere. It alters the regional energy budget and suppresses the convection needed for rainfall. In a small but physically tangible way, each event makes the next dry day more probable than the one that came before. The atmospheric recipe identified by Cook and his colleagues in 2009 did more than just outline how a dust bowl could begin. It described how, once started, a dust bowl sustains itself. That very mechanism is now active, which raises a critical question. How far is the system from a threshold where these feedbacks become self-reinforcing, on a scale we can no longer easily contain? Part 7. The return of continental scale dust transport. On May 11th, 1934, a colossal dust storm that began on the northern plains swept eastward, traversing the entire continent. By the time this immense cloud reached the east coast, it was carrying an estimated 350 million tons of precious topsoil across 2,000 miles of American landscape. Dust from the plains settled on the decks of ships far out in the Atlantic Ocean. It fell like a strange, gritty snow on Washington, D.C. In Chicago, residents watched as the midday sky dimmed to a murky twilight. And in New York City, people awoke to find a fine layer of prairie soil coating their windowsills. The sheer size of the storm and the volume of material it carried fundamentally shifted the public and political perception of what was unfolding in the Great Plains. This was the moment the Dust Bowl stopped being a distant, regional agricultural story and became an undeniable national crisis. For dust to travel on such a continental scale, a specific set of ingredients must come together in a precise sequence. First, you need a source region with a vast expanse of exposed, loose, fine-grained soil. Next, you need wind velocities at the surface that meet or exceed the threshold for mobilizing those particles, typically around 12 to 15 miles per hour for fine silt and clay. Then, the atmospheric structure must be able to lift these mobilized particles vertically, carrying them into higher wind levels, where they can be transported over long distances without settling back to Earth. Finally, the source region itself must be large enough that its supply of material is not depleted before the atmospheric pathway can carry it across the continent. It is a delicate yet powerful atmospheric choreography. In the early months of 2026, NASA satellite imagery began to capture dust transport events that, while not yet matching the historic scale of the 1934 storm, were demonstrating the same fundamental pattern. Material originating in the Texas and Oklahoma Panhandle region was being carried eastward by the prevailing atmospheric circulation, moving deep into the central and eastern United States. The evidence was clear. The source region was active. The wind was performing its work. The atmosphere was doing what it has always done. The question was no longer about potential, but about observed reality. Whether we are approaching the threshold for events comparable to the great continental storms of the 1930s is a matter of genuine uncertainty, and it is vital to be honest about that uncertainty, rather than overstate the case. The conditions required for an event on the scale of 1934 are truly extreme. The degree of soil exposure would need to be substantially greater than what currently exists, and the atmospheric setup would need to be perfectly aligned. Even during the Dust Bowl itself, These massive storms were rare. They did not occur every season. And yet, here is what the current satellite record tells us with certainty. The source region is active in a way it has not been for decades. The storms now being produced are large enough to be clearly visible from orbit and powerful enough to push air quality in major Texas cities beyond every threshold. The EPA's index was designed to describe the transport pathway, that atmospheric corridor that carries Great Plains material eastward, is fully functional. We are not at 1,934. But the question the current data poses is not whether we could get there, but what would need to change to make that outcome likely. Based on everything the 2009 research tells us, the answer is unsettlingly little. Continued drought, continued soil exposure, and a strong synoptic wind event. The system is closer to that threshold than at any point since the 1950s. Every major dust mobilization we see now is another data point, confirming that the mechanism is running, that the recipe is back. This is not a theoretical concern. It is an observable physical reality. Part 8. 400. When measurement systems break. The EPA's Air Quality Index, or AQI, was designed with a clear purpose: to communicate health risks to the general public in an easily understood format. The scale runs from 0, representing clean air, through a series of color-coded tiers. It reaches a level the agency designates as hazardous for values above 300, and the published scale officially tops out at 500. At an AQI of 500, the guidance is unambiguous. Everyone should avoid all outdoor physical activity. Sensitive groups are advised to remain indoors, and for those with respiratory conditions, it is a situation to be treated as a medical emergency. During the storm events of March 2026, Lubbock, Texas, registered an air quality index of approximately 1,400. That number is not merely a different tier on the same scale. It represents a reality operating in a range the scale was never intended to reach. The designers of the AQI were not planning for conditions that would exceed their own worst-case scenario by a factor of nearly 3. The instruments themselves were still functioning, measuring the particulate matter accurately. The problem was that the framework built to interpret their measurements, the scale itself, was constructed with an implicit assumption that American air quality, even at its most extreme, would stay within a certain boundary. Lubbock had gone far outside that boundary. From the standpoint of basic respiratory medicine, the health implications of such conditions are not difficult to project. Particulate matter at those concentrations, especially the fine PM2, 5 particles small enough to penetrate deep into lung tissue, causes acute irritation of mucous membranes and significant bronchial inflammation. With prolonged exposure, it can trigger conditions analogous to what was documented in the 1930s as dust pneumonia. In that era, dust pneumonia was a real and terrifying clinical phenomenon. It was an acute respiratory illness brought on by the inhalation of fine soil particles, which caused severe inflammation and fluid accumulation in the lungs. It was a condition that killed people, and it was particularly fatal for children. The conditions that materialized in Locke during March of 2026 were not an exact replica of those that gave rise to the dust pneumonia of 1935, but they were undeniably operating within the same physical regime. We have moved beyond the point of simple academic comparison. The planetary system itself is now generating measurable, classifiable extremes that overwhelm the very frameworks we constructed to track them. This unsettling reality is the core of our story, and its most potent symbol is a single, borrowed word, haboob. The use of this term serves as a critical red flag, not a mere curiosity. The National Weather Service is a federal agency whose meteorologists are bound by a professional duty to be precise. Their vocabulary is not chosen for dramatic flair, it is a tool for accuracy. Therefore, when the NWS office in Amarillo began to issue formal haboob warnings for events on the southern plains. This was a deliberate, technical classification. It was their conclusion, after consulting instruments and direct experience, a recognition that the meteorological events they faced required a new and more fitting descriptor. A haboob is a specific, intense dust storm born from collapsing thunderstorm outflows in arid deserts. The term, from an Arabic word for strong wind, entered meteorology via British observations in Sudan. It became standard for such events in the Sahara, the Arabian Peninsula, and the American Southwest, where Phoenix regularly experiences them from the Sonoran Desert. The essential ingredients are a towering wall of dust, ferocious winds from a downdraft, and a vast supply of loose, fine-grained material on the ground, ready to be mobilized. But the Texas Panhandle and southern Oklahoma are not the Sonoran Desert. They are not the Sahara. Historically, these regions have never been the kind of environment that generates haboob-class events. The fact that NWS Amarillo, an office for agricultural plains, not a desert, is now employing this vocabulary is a direct meteorological statement. It tells us the surface conditions of the southern plains have changed so fundamentally that their weather now mimics that of a true desert. The operational forecasters have adapted their language to a physical shift that public discourse and policy have yet to acknowledge. This gap between observation and action is a dangerous part of the story. The forecasters are sounding an alarm that the system has changed. The vital question remains whether anyone is listening. A common point of optimism when comparing today to the 1930s is vegetation. The argument holds that while the Dust Bowl's catastrophic ploughing removed native sod across millions of acres, today's landscape retains some residual plant cover. Though not healthy or resilient, it exists. This observation is accurate but dangerously incomplete, as it fails to account for the transformative role of modern wildfire. In the first quarter of 2026 alone, an astonishing 1,100,000 acres burned across the southern plains. These were not typical wildfires. They were supercharged by the very conditions producing the dust: extreme drought, low humidity, relentless winds, and a vast accumulation of dead vegetation that the drought had killed. By any historical measure, the fire conditions were extraordinary. The reason this matters so profoundly is that fire eradicates the very residual vegetation that drought had only weakened. When a fire sweeps through, it incinerates the organic surface layer, the litter, fungal networks, and decomposed matter that binds soil particles together. What remains is sterile mineral soil, with minimal binding, minimal moisture, and no protection from the wind. In every way that matters physically, this scorched earth is indistinguishable from a ploughed field. The wind makes no distinction between a tilled field and a burned landscape. In both cases, it finds loose, unprotected material ready to be lifted. This dynamic creates a feedback loop wholly distinct from the 1930s, and it appears to run significantly faster. Fire exposes soil, enabling dust mobilization. This dust can suppress rainfall, intensifying the drought. The worsening drought kills more vegetation, creating fuel for more fires, which in turn expose more soil. The cycle can accelerate in a way the simple drought plus plowing dynamic of the past could not, because fire removes protective cover in hours, not months. Critically, the 2026 fire season is occurring within the same drought, across the same region where ocean patterns and land degradation are already primed. The recipe for disaster that Benjamin Cook and his colleagues identified in 2009 was based on the variables of the 1930s. The current system appears to have added a powerful new amplification pathway. This raises an uncomfortable possibility. If the 1930s configuration was enough to produce Black Sunday and a decade of catastrophe, what will a version with an added fire dust feedback loop produce? We have no historical precedent for that question. We may be developing one in real time. Disturbingly, this threat is not being clearly articulated by federal agencies, leading to a part of the story beyond climate, something more structural and difficult to explain. This brings us to a profound paradox at the heart of the modern high plains. Why does the Texas Panhandle, along with the adjoining plains of Oklahoma, Kansas, Colorado, and New Mexico, remain one of the most intensively farmed regions in the United States? This agricultural engine persists despite the area suffering through the nation's most severe and sustained drought. The explanation for this seeming impossibility is not, as one might first assume, a story of ecological resilience. The landscape of the American Great Plains can be deceiving. What appears to be a verdant, well-watered agricultural heartland is not, in fact, enjoying a temporary break from a dry spell. Instead, its apparent health is drawn from a hidden source, the Ogallala Aquifer. This is a colossal underground reservoir of fresh water, stretching across some 174,000 square miles from South Dakota down to the Texas Panhandle. To grasp its scale, consider that it holds more water than Lake Huron. Since the middle of the 20th century, this aquifer has been the lifeblood of high plains agriculture. By pumping this ancient water, farmers can provide irrigation that allows crops to flourish even when surface conditions are catastrophically dry. This hidden water source is the fundamental reason the southern plains appear more stable today than they did during the 1930s. Irrigated fields can endure drought conditions that would have destroyed the rain-fed farms of the past. The lush green circles visible from space, even in the midst of a 6-year drought, exist only because water is being drawn from thousands of feet below ground. On the surface, the system seems to be working perfectly. The soil looks productive, and the farms appear to be thriving. What this surface-level illusion of stability conceals, however, is the staggering rate of the water's depletion. The Ogallala Aquifer recharges at an exceptionally slow pace, accumulating only fractions of an inch of water per year across most of the high plains, a rate that reflects the region's naturally low precipitation. Yet, the water is being pumped for irrigation at a speed that, in some parts of the Texas Panhandle, is estimated to exceed this natural replenishment by a factor of 800%. This raises a critical point about how we view this resource. The aquifer is not being used sustainably, it is being mined. Like any finite resource that is extracted far faster than it is replaced, its supply is steadily dwindling. In the southern high plains, which includes the historical epicenter of the Dust Bowl and the heart of the current drought, the timeline is becoming alarmingly short. At current rates of extraction, it is estimated that some areas have less than 25 years of usable water left for irrigation. For some communities, that threshold has already been crossed. Wells that once reached water at just 60 feet in the 1950s now must be drilled to 300 feet or more. As the water table drops, the cost of pumping escalates dramatically, making what was once marginal agriculture progressively less viable from an economic standpoint. This reality reframes the entire question of a modern dust bowl. The Ogallala Aquifer is not a permanent solution to the underlying environmental conditions of the region. It is merely a delay mechanism. It is allowing industrial agriculture to persist on land that, without this artificial support, would have already reverted to the bare, unprotected state that the 1930s drought created through different means. But this delay is not indefinite. It operates on a strict timeline. The moment will come when the irrigated agriculture of the Texas Panhandle can no longer be supported by the aquifer. This could happen because the water is physically gone, because pumping costs become prohibitively expensive, or because new policies restrict its extraction in response to the drought. When that happens, the land that has been kept under crop cover by irrigation will lose that protection. This transition will not be gradual. It will be terrifyingly abrupt. The shift from irrigated cropland to exposed, vulnerable soil happens the moment a farmer decides to stop pumping, a decision that can be made in a single season. The farmers of the 1930s Dust Bowl era did not have this variable. Their agriculture was entirely rain-fed. When the rains failed, the crops withered, the land was abandoned, and the soil was left exposed to the wind. The current system has a buffer, but that buffer is temporary, and it is shrinking. As time passes, the system it supports does not grow more resilient. On the contrary, it becomes more fragile and more vulnerable to a sudden collapse. The Ogallala is not saving the High Plains from a new Dust Bowl. Instead, it is setting the stage for the eventual return of Dust Bowl conditions to be far more sudden and shocking when it finally arrives. An illusion of stability, in this respect, can be more dangerous than visible instability, as it postpones our recognition of the problem until the solutions are more costly and the collapse is more severe. There is another critical factor at play, the warmer baseline problem. The Dust Bowl of the 1930s occurred during a period when global average surface temperatures were already slightly elevated compared to the pre-industrial baseline. However, that elevation was dramatically lower than what we are experiencing today. The best estimates from climate reconstructions and historical records place the global average temperatures of the Dust Bowl era at roughly 0.1 to 0.3 degrees Celsius above the pre-industrial average. By 2026, that figure has climbed to approximately 1.3 to 1.5 degrees Celsius above pre-industrial levels, a warming effect that is roughly 5 times greater. This is not just a background number, it has profound physical consequences. The reason this matters so much is that temperature directly governs the physics of a drought. This is a matter of basic thermodynamics. Described by the Clausius-Clapeyron relationship, warmer air has the capacity to hold more water vapor at saturation. This means that a warmer atmosphere has a higher evaporative demand. It is, in a sense, thirstier. In practical terms, this means that a given shortfall in precipitation will produce a much more severe drought under a warmer baseline. The same amount of rainfall that might have maintained marginal soil moisture in the 1930s now evaporates more quickly. It leaves less residual moisture behind in the soil profile and produces the symptoms of a serious drought much more rapidly. For a drought to be more damaging, it doesn't have to be deeper in terms of rainfall deficit. It simply has to occur in a warmer atmosphere. This calculation is not merely speculative. Scientists can quantify this effect using a metric known as the Palmer Drought Severity Index, or PDSI, which integrates both precipitation and temperature into its assessment of drought conditions. When researchers apply current temperature levels to the historical precipitation deficits of the past, the resulting PDSI values are consistently more extreme. The same lack of rain would have produced a far more devastating drought in our warmer climate. The current 6-year drought unfolding across the southern plains is happening in an atmosphere that is substantially warmer than that of the 1930s. As a result, a drought that is physically similar in its origins now hits much harder. It is vital to maintain a sense of nuance here, as this point is often misunderstood in public discussions. Climate change is not the direct cause of the current drought conditions. The primary driver is a configuration of the oceans, a cool Pacific and a warm Atlantic that has occurred multiple times in the instrumental record, long before the current era of rapid warming. Similarly, the land degradation that makes the soil vulnerable has been occurring since the 1980s. Driven by economic and policy factors, not primarily related to global temperature, the fundamental recipe for a dust bowl does not require climate change to exist. What climate change does, however, is act as a powerful amplifier for that recipe. It takes a drought that the ocean configuration would have produced anyway and makes it significantly more intense. It takes exposed soil that land use policies have left unprotected and causes it to lose its moisture much faster. Climate change therefore, is the great multiplier, turning a serious challenge into a potentially catastrophic one. It takes every component of the Dust Bowl recipe and makes it more potent, raising the stakes for a region already living on borrowed time and borrowed water. The research conducted by Cook identified a critical feedback loop, one that is self-sustaining. A warmer baseline climate gives this dangerous cycle a more favorable environment in which to operate. It is a subtle but profound distinction to make. This background warmth is not the origin of the crisis, but its amplifier. In any complex system that is already functioning near a critical threshold, such an amplifier is anything but a minor detail. It intensifies every single variable in the delicate equation, transforming what might have been a close call into a full-blown disaster. The Dust Bowl of the 1930s prompted a massive human migration, displacing an estimated 2.5 million people from the southern plains. This was the exodus that Steinbeck so powerfully documented in Time's The Grapes of Wrath, as families journeyed west along Route 66 toward California. While that displacement was a catastrophe in human terms, it unfolded across a landscape that was, by today's standards, quite sparsely inhabited. In the 1930s, the Great Plains were a region of small towns and farming communities, a rural population spread out over a vast area with a relatively low density. The situation today is dramatically different. The modern High Plains and the surrounding areas are home to major metropolitan centers. Lubbock, Texas, for instance, has a population of around 260,000 people, while Amarillo has more than 200,000. Oklahoma City, which lies directly within the drought zone, is now home to over 600,000 residents. These cities were either much smaller or did not exist in their current form during the original Dust Bowl era. Consequently, the vast infrastructure they rely upon, from highways and airports to power grids and water treatment facilities, was never designed or stress-tested for the kind of conditions that are re-emerging. This includes air quality indices soaring to 1,400, near zero visibility, causing multi-vehicle pileups, and the sustained contamination of air intake systems with fine silicate dust. The public health consequences of these modern dust events scale directly with the population. More people breathing the same degraded air inevitably leads to more acute respiratory episodes, more emergency room visits, more lost days of school and work, and more cumulative, long-term lung damage. The economic disruption from these new storms, which includes flight cancellations, highway closures, and damage to agricultural equipment, now ripples through a far more complex and densely interconnected system than existed in the 1930s. This raises a sobering question. How does the same environmental recipe produce such a different outcome? The climate science may be the same, but with a much larger human population in its path, the calculus of consequence has changed entirely. Part of this story centers on a single day, April 14th, 1935. On that day, which came to be known as Black Sunday, a dust storm of exceptional scale and ferocity swept across the southern plains. It reduced visibility to nearly zero across a region hundreds of miles wide, lifting thousands of tons of precious topsoil into the atmosphere. In the context of the preceding 3 years, the storm itself was not entirely unusual. What set it apart was its sheer size, its intensity, and the fact that it struck on a Sunday afternoon, when many people were outdoors rather than sheltered inside their homes or workplaces. The photographs taken that day became iconic. Towering walls of dust, dwarfing buildings, and people running from a moving, brown apocalypse. The images shocked the nation. But what matters even more than the shock is what happened next. The government's response was extraordinarily fast, by any measure. Within mere months of Black Sunday, the Soil Conservation Service was created in 1935. Hugh Hammond Bennett, a scientist who had warned about soil erosion for years before the Dust Bowl proved him right, was appointed its first chief and acted with incredible urgency to deploy every available tool. The Great Plains Shelter Belt, a massive tree planting project, was funded and operational within just 2 years. The concept of a conservation reserve, which involved paying farmers to remove fragile land from production, was developed and implemented within a few years. Emergency soil surveys, erosion mapping, and educational programs for farmers were established across the affected region in a fraction of the time such federal initiatives typically require. This remarkable speed reflected 2 key factors: the undeniable physical visibility of the crisis, and the fact that policymakers in 1935 had personal, living memory of the problem as it developed in real time. The administration of Franklin D. Roosevelt included agricultural officials who had been directly engaged with soil erosion issues for years. Their scientific understanding, while incomplete by modern standards, was sufficient to identify both the mechanism and the solution. Crucially, there was also the political will to act on a scale that matched the problem. Decades later, however, that institutional memory of the Dust Bowl has all but vanished, fading into generational history. The people who lived through it are gone. The very policy infrastructure it created, the Soil Conservation Service, later reorganized into the Natural Resources Conservation Service, the Conservation Reserve Program, CRP, and the Shelter Belt programs, has been weathered by decades of shifting budget cycles, administrative reorganizations, and changing political winds that have progressively diminished its scale and influence. The decline in CRP enrollment that we see today is a symptom of this pattern. It wasn't a sudden policy reversal, but rather a slow erosion of commitment, driven by competing budget priorities, evolving agricultural economics, and a simple lack of anyone in the room who remembers why those programs were created in the first place. The Environmental Working Group has documented this trend in federal agricultural conservation spending over recent decades, and the picture it paints is consistent. In real terms, the very programs designed to prevent a recurrence of the Dust Bowl have been systematically underfunded. Instead, funding has shifted toward programs designed to compensate farmers times after times their losses have already occurred. This reveals a fundamental change in philosophy, a pivot from prevention to response. At the heart of this shift lies a profound irony. Our scientific understanding of what prevention requires has never been better. The 2009 research gave policymakers a precise, validated model of how this environmental system fails. Modern data systems, from drought monitoring and satellite imagery to ocean temperature tracking, give current officials real-time visibility into whether the conditions identified in that model are beginning to align. The tools to recognize and measure the risk are in our hands. What appears to have eroded is the institutional will to use them at the scale that the risk demands. In the field of organizational behavior, there is a concept known as collective memory, the shared knowledge and learned responses that become embedded in an institution's structures over time. The original Soil Conservation Service was a powerful carrier of this collective memory, an organization built to hold on to the hard-won lessons of the Dust Bowl. The question we face now is whether that memory can be recovered before it is too late. The immense human suffering of the 1930s gave rise to hard-won lessons, once translated into powerful operational programs with dedicated staffing and budgets that endured for generations. However, the gradual dismantling of these agencies and the weakening of their programs signifies a kind of institutional forgetting. While the knowledge is preserved in archives and papers, the ability to act upon it at a meaningful scale is not what it was in 1950, 1960, or 1975. This growing chasm between what we understand and what we can do is no historical accident. It is the direct outcome of deliberate policy decisions. This gap brings us to the core question of our story. Not why these environmental conditions are re-emerging, but why a commensurate response is so conspicuously absent. Part 15. Insurance versus prevention. One of the most significant and politically resilient components of American agricultural policy is the federal crop insurance program. Each year, the government provides substantial support, subsidizing around 60% of the insurance premiums paid by farmers. With federal spending averaging between $8 and $10 billion annually, it offers a crucial safety net, protecting incomes when crop yields drop from perils like drought, floods, or pest damage. The program is immensely popular with farmers, enjoys widespread political backing, and is now fundamentally woven into the farm economy. Yet, this same program has become a powerful driver of the land use incentives contributing to the conditions at the heart of this story. The mechanism is straightforward. Crop insurance does not require participating farmers to implement soil conservation practices for coverage. A farmer can cultivate land that federal agencies classify as highly erodible, vulnerable to wind and water, and still receive subsidized premiums without any commitment to erosion control. When the crop fails, the insurance policy pays out. The farmer is compensated financially, but the land remains bare, unprotected, and exposed to the next drought. A damaging cycle is thus established and repeated. In direct contrast stands the Conservation Reserve Program, or CRP. This initiative pays farmers not times to plant their fields, leaving them under a protective cover of grass or other vegetation. The goal is to preserve the soil's structure and the plant life that helps it resist wind erosion. The CRP provides a rental rate per acre per year to keep land enrolled. For a farmer, the choice becomes a simple economic calculation. Does the CRP payment outweigh the potential profit from farming that land, especially when factoring in the safety net of subsidized insurance? In recent years, across large areas of highly erodible land in the southern plains, the scales have tipped. The financial backstop from crop insurance has made farming marginal land more profitable than enrolling it in the CRP for conservation. This dynamic is not a secret. Agricultural economists have written about it extensively. The Government Accountability Office has noted it, and conservation organizations have argued for a solution. Despite this awareness, the policy response has been remarkably limited, suggesting a deep inertia within the system. The consequence is a federal agricultural support system that, taken as a whole, financially incentivizes putting vulnerable land into crop production. It then financially compensates the farmer when that land fails, while the soil itself is allowed to degrade further, becoming more fragile with each passing season. It is a system that appears to work at cross purposes with itself. This modern approach stands in stark contrast to the policies enacted after the original Dust Bowl. The response in the 1930s was not focused on compensating farmers for losses, but on preventing them by fundamentally changing practices on the land. The Soil Conservation Service wasn't writing checks for fields that had blown away. It deployed technical staff to farms to demonstrate contour plowing, establish cover crops, plant shelter belts, and develop conservation plans to prevent fields from eroding in the first place. The incentive structure was prevention-oriented. Money flowed toward actions that reduced vulnerability, not actions that compensated for it after the fact. This shift from a prevention-oriented to an insurance-oriented policy is not unique to the United States. It reflects a broader ideological movement over decades toward market-based mechanisms and away from prescriptive land management. While this shift has legitimate arguments, its practical outcome in the southern plains is clear. The land is more exposed than it would be under a prevention-focused regime, and the cost of that exposure is socialized through insurance payouts rather than prevented through conservation investment. The tab for the next Dust Bowl, in other words, is already partially open. The question is how large it will grow before the policy calculus changes, a change that may depend on a decision that has not yet been made. To state clearly what is actually happening. Part 16. Why no one is calling it a Dust Bowl. Let us spend some time with this central question, as it deserves more than a rhetorical gesture. The science is clear, the conditions are documented, and the comparison to the historical mechanism is explicit in peer-reviewed literature. And yet, as of April 2026, a profound official silence persists. No major federal agency, not NOAA, the USDA, the EPA, or the National Drought Mitigation Center, has issued a statement using the words Dust Bowl to describe the current situation. No senior administration official has held a press conference drawing the comparison, and no congressional hearing has been convened to ask if the conditions have reassembled. This silence itself begs the question, why? The answer is not a simple one, as the reality is more complicated than any single explanation can capture. A primary reason for this silence is institutional fragmentation. The data that, when assembled, tells the Dust Bowl story is distributed across multiple agencies with different mandates, communication cultures, and political reporting chains. NOAA tracks ocean temperatures and drought. The USDA tracks agricultural losses and CRP enrollment. The EPA tracks air quality, while NASA's Earth Observatory produces satellite imagery. The Natural Resources Conservation Service tracks soil erosion. Each of these agencies sees its own piece of the picture clearly, but no single entity is tasked with putting them all together. While the data points to a gathering storm, no single government body has the explicit duty to weave those points together into the comprehensive story that Cook and his colleagues published in 2009. An academic researcher enjoys a certain freedom to interpret what the data means as a whole. A freedom an agency official, bound by a specific mandate, often lacks. This raises a fundamental question about how our institutions are structured to perceive large-scale threats. A second reason for this quiet is the management of economic and political risk. The markets for agricultural commodities are highly susceptible to narrative. An official government declaration that Dust Bowl conditions have returned to the southern plains would have profound consequences. It could affect crop insurance, the value of land, commodity prices, and agricultural lending, potentially setting off market reactions that are entirely separate from the physical conditions on the ground. There is a deeply held belief in agricultural policy that words carry immense weight and that labeling a crisis can sometimes accelerate the very dynamics it describes. Whether this caution justifies silence in the face of grave risk is another matter, but it is a powerful factor in the institutional calculation. A third explanation involves liability and the obligation to respond. If the government were to formally acknowledge that Dust Bowl conditions are back, and that federal programs like crop insurance and CRP funding are contributing factors, it would create an implicit duty to act. Such an admission is not a neutral statement. It generates immense political pressure for a response at a scale that matches the problem. Mobilizing a massive, well-funded soil conservation effort, similar to what occurred in 1935 and 1936, would be enormously expensive and politically fraught. It would also mean reversing policy directions that have been entrenched for decades across multiple administrations. The fourth reason lies in the distinction our media and political systems make between an event and a system. Modern communication is built around discrete, definable events, a particular storm, a specific market crash, a single fire. The story of the Dust Bowl, as defined by the Cook research, is not an event but a system state. It describes a set of interacting conditions that have aligned into a configuration known to produce catastrophic results. This kind of systemic story is far more difficult to report on, to communicate, and to motivate action around than a single dramatic incident. A Habu warning or an EQI of 1,400 are events. The slow reassembly of the Dust Bowl recipe is a system condition. And our public and political attention is far better designed to react to the former than the latter. When you assemble these explanations, what emerges is not a conspiracy of silence or a deliberate suppression of truth by malicious actors. Instead, we see a kind of structural silence. It is the natural output of fragmented institutions, misaligned incentives, cultures of risk-averse communication, and the profound difficulty of compelling political systems to address system-level dangers instead of just event-level shocks. The knowledge is there, the data exists. The framework for understanding its meaning was published 16 years ago, yet the system is not responding at the necessary scale. This isn't because no one knows. It's because the very way our system is organized makes it nearly impossible for knowledge to translate into action before a catastrophe makes the cost of inaction undeniable. This gap between knowing and acting is the true story, and understanding this gap is the first step we must take if we hope to close it. Whenever conditions become alarming enough that official channels no longer offer satisfying explanations, alternative theories begin to multiply. This is as true for dust storms as it is for anything else, and it is an understandable human response. When you witness a city of 260,000 people vanish behind a brown wall of dust at midday, and the official response feels like little more than a drought monitor update and a quiet Habu warning, the mind naturally searches for a narrative that matches the terrifying scale of the event. I understand that impulse completely. The problem, however, is that getting the explanation wrong doesn't just lead to flawed conclusions. It leads to flawed responses. In a situation where the correct response is already dangerously overdue, the wrong explanation is not a harmless diversion. It is a costly delay. So it becomes necessary to walk through some of the alternative theories that have circulated and explain why they are insufficient. The goal is not to dismiss the people asking legitimate questions, but to show that a correct explanation, grounded in peer-reviewed literature, already exists, one that points toward real solutions we could deploy, if only enough people understood what was truly happening. The weather modification theory is a recurring theme whenever drought and atmospheric anomalies converge. It deserves a serious answer, not a dismissive one, because it is built around a kernel of demonstrable fact. Technologies for atmospheric modification are real. Cloud seeding is a documented and actively used practice. Dozens of state and local agencies across the American West use silver iodide dispersal to try and enhance precipitation over watersheds and reservoirs. The United Arab Emirates operates one of the world's most advanced national cloud seeding programs, and China has invested billions in its own weather modification infrastructure. The technology is not science fiction. It is deployed in the real world, and governments are not always transparent about its use. On this point, the premise of the theory is accurate. Where the theory falls apart, however, is not in the realm of politics, but in the unyielding laws of physics. The critical issue is the sheer scale of energy involved. When we compare the energy driving the current 6-year multi-state drought across the southern plains with the energy of any existing or even theoretically plausible atmospheric modification technology, we find a staggering difference of approximately 10 to 12 orders of magnitude. It is vital to grasp the immensity of that number. An order of magnitude is a factor of 10. 10 orders of magnitude is a difference of 10 billion times. 12 orders of magnitude is a trillion times. The ocean temperature anomalies driving the current atmospheric patterns involve the redistribution of thermal energy across millions of square miles of the ocean's surface, down to depths of hundreds of meters, and over time, scales stretching from months to years. This is a planetary engine at work, and its power dwarfs our current technological capabilities to a degree that is almost difficult to comprehend. The sheer energy involved in this redistribution of weather patterns is staggering. It eclipses the combined output of every power plant, every atmospheric heater, and every other human-operated weather intervention system on Earth by a factor that is almost impossible to comprehend. This clarifies that the issue we face is not a problem of technology, funding, or secrecy. It is a problem of fundamental climate physics. The ocean is behaving as the ocean does, powered by thermodynamic processes that unfold on a planetary scale. No technology operated by any known entity can generate or maintain a forcing of that magnitude. So, when someone suggests that a drought is manufactured, the most effective response is not to debate intentions. Instead, it is to ask them to explain the energy budget. The numbers themselves resolve the argument. A second explanation proposes that what we are witnessing falls within the normal range of weather variability on the plains, that this is merely a severe dry spell, not something that justifies the level of concern this story conveys. This view is contradicted not by a single piece of data, but by the convergence of all data sets at once. This distinction is critical because individual data sets can indeed be selectively interpreted to support nearly any desired conclusion. 1 year of rainfall below the average is normal. A single haboob or dust storm in the Texas Panhandle, though rare, is not out of the question. A single season with high withdrawals from the Conservation Reserve Program is a matter of agricultural policy, not an impending crisis. Viewed in isolation, any of these data points could be explained away as part of historical variability. What cannot be rationalized in this way is all of them happening together, tracking in perfect alignment with the specific, multivariable recipe that Cook, Miller, and Seeger identified in 2009 as the documented cause of the Dust Bowl. The evidence is a formidable list. 6 straight years of drought, multi-decade lows in CRP enrollment, record-breaking temperatures in the North Atlantic, a Pacific Ocean transitioning from La Niña to a neutral state, air quality events so severe they broke monitoring equipment, haboob-level storms in farming regions, and satellite-visible dust transport on a continental scale, originating from the same region as in the 1930s. The likelihood that this exact combination of factors would assemble by chance at the very moment the ocean's configuration matches the Dust Bowl's trigger pattern is not a matter for debate. It is a statistical claim that simply does not hold up to scrutiny. While each variable has appeared before on its own, the pattern they are now forming together has a name, a known mechanism, and a known, devastating historical precedent. Normal variability does not create this alignment. The Dust Bowl recipe does. The third explanation is, in some respects, the most compelling because it starts from a correct premise but extends it too far, ultimately arriving at the wrong conclusion. The argument that climate change is the sole cause, framing everything now visible in the southern plains as a direct result of global warming, is not mistaken about the role of climate change. It is, however, mistaken about its primacy. As we've explored, the warmer baseline temperature acts as a powerful amplifier. It makes every drought more intense, every soil moisture deficit more critical, and every feedback loop more energetic. Climate change is undeniably real. Its effects are measurable, and it is making the present situation far worse than the same conditions would have been 50 years ago. But climate change did not create the specific ocean configuration that is driving this drought. That pattern has appeared throughout the instrumental record, during climate states both cooler and warmer than today's, and it will continue to occur in multi-year cycles no matter what happens to the global average temperature. Furthermore, climate change did not remove 11 million acres from the Conservation Reserve Program. That was a direct result of agricultural policy. Climate change did not dismantle the extensive shelter belt infrastructure that was planted after 1935. That was a consequence of mechanized farming, economics, and budgetary choices. And climate change did not structure the federal crop insurance program in a way that actively incentivizes planting on marginal, vulnerable land. That was a legislative decision. The degradation of the land, which transforms a drought into a dust bowl, is the second crucial ingredient in the recipe. It is the one element without which the ocean's forcing produces hardship, but not a full-blown catastrophe. This degradation is driven by specific, identifiable, and reversible human decisions that have no connection to atmospheric carbon concentrations. This distinction is enormously important when we ask what can be done. If the story is simply climate change caused this, then the response requires a 20 to 30-year decarbonization project, demanding global coordination, massive infrastructure investment, and a political consensus that has proven incredibly difficult to build. While that response is vital for countless other reasons, it will not protect a single acre of Texas topsoil this spring. However, if the story is that the Dust Bowl recipe is reassembling and we can interrupt it, the path forward changes dramatically. By restoring CRP enrollment, reinforcing shelter belt infrastructure, and realigning crop insurance incentives to favor conservation, the response can be implemented on the timeline of a single Farm Bill cycle. The tools and programs already exist. The institutional capacity, though diminished, is still present. This response is available to us now, at a cost that is merely a fraction of the damage it would prevent, assuming the diagnosis is correct. Getting the explanation wrong does more than just foster an incorrect understanding of the situation. It effectively closes the door on the most actionable solutions at the precise moment when action is most desperately needed. The recipe is known, the ingredients are gathered. The only thing still missing is the collective willingness to call the phenomenon what it is and to respond accordingly. This brings us to a haunting question from our past. Could Black Sunday happen again? April 14th, 1935. That date is remembered by meteorologists and historians as Black Sunday, the single most severe dust event of the entire Dust Bowl era and one of the most extreme weather events ever documented in North American history. But before we explore what took place on that day, it is essential to understand the conditions in the weeks and years that preceded it. The storm itself was a matter of hours, but the environment that made it possible had been building for a very long time. By April of 1935, the southern high plains had already suffered through 5 consecutive years of rainfall far below the average. The stage was already set. Across millions of acres, the very fabric of the land had been undone. The native grasses that had anchored the soil for millennia were gone, systematically replaced by wheat fields. When the wheat failed, and farmers could no longer afford to replant, the land was left with nothing at all. What remained was a vast expanse of loose, dry topsoil on a flat, open plain, stripped of its windbreaks, its root systems, and the moisture that once gave it cohesion. In the most literal sense, the landscape had been prepared for a catastrophe. It was simply waiting for the right wind. On April 14th, 1935, that wind arrived. A powerful cold front generated the storm in the northern plains, driving it southward and eastward, with surface winds gusting to 60 miles per hour. It manifested as a colossal wall of dust, approximately 800 meters wide and towering several miles into the sky, advancing across the plains at the same relentless speed. Those who saw it approach described a moving cliff, a vertical, brownish-black wall stretching from the ground to the heavens, moving toward them faster than a person could run. Within minutes of its arrival, noon turned to a profound night, a darkness far deeper than any overcast afternoon. Visibility plunged to absolute zero. On the roads, drivers had to abandon their cars, unable to see even the hoods of their own vehicles. In the fields, Animals suffocated. People caught outside were blinded and lost, some resorting to crawling on their hands and knees, desperately trying to follow fence lines back to the safety of shelter. Even inside homes, dust poured through every crack and keyhole. Families huddled in the dark, stuffing wet rags around doors and windows, listening to the howl of the wind and waiting for the ordeal to pass. The color of the sky that day became the defining image of an entire era. Witnesses described it as black, as brown-black, as the color of death, a shade for which ordinary experience had no name. It is this image, not the poverty or the migration, that still endures when those who know their history hear the words Dust Bowl. An event of this magnitude does not simply pass, it leaves an indelible mark on culture and memory. Woody Guthrie, who was in Pampa, Texas, watched the storm roll in and immortalized it in his song, So Long It's Been Good to Know Ya. A federal government photographer, Arthur Rothstein, captured images of families fleeing the wall of dust, photographs that would become some of the most recognized in American history. And it was a young journalist named Robert Geiger, reporting from the region, who sent a dispatch east that contained the first recorded use of the phrase Dust Bowl in print. The storm did more than just happen. It gave a name to an age of hardship. In retrospect, the conditions that produced Black Sunday were not particularly exotic or mysterious. The recipe for such a disaster was tragically simple. First, you needed a vast area of exposed, loose, fine-grained soil, which years of aggressive plowing and prolonged drought had provided across millions of acres. Next, you needed a strong frontal boundary, capable of generating intense surface winds, a feature the weather pattern of April 14th delivered in abundance. You also required exceptionally dry atmospheric conditions that would prevent the mobilized dust from being washed out by rain, allowing it to travel for hundreds of miles, a condition met by a 6-week dry spell. Finally, the source region had to be large enough to continuously feed the storm's mass. The degraded high plains offered more than enough material to sustain the storm's structure over its entire journey. The true tragedy, perhaps, is that these prerequisites were not complicated. They had been assembling, visibly and documented, for years before the storm finally arrived. This brings us to a critical and delicate question. Could these conditions reassemble in the year 2026? It is a question that demands a careful and honest answer, as both overstatement and understatement carry significant costs. To overstate the risk is to invite panic, which can discredit legitimate concerns. To understate it, however, is to repeat the very error that left people so unprepared on that Sunday in 1935. Here, then, is the precise and accurate answer. Not all of the prerequisites for Black Sunday are currently present at the same scale as they were in 1935, and this distinction is crucial. Today, soil exposure across the southern high plains is substantial and growing, but it does not yet match the near-total coverage of the plowed and abandoned landscape of the 1930s. Some perennial vegetation remains, providing partial cover over a meaningful portion of the land. This cover is not healthy, nor is it resilient. It has been diminished by 6 straight years of drought and damaged by the 1.1 million acres of wildfire that burned in the first quarter of 2026 alone. Yet, it is still cover, and even marginal cover matters in these delicate calculations. Furthermore, the specific atmospheric setup required for a Black Sunday class event is itself a rare occurrence. It demands a precise combination of a weather front's timing, trajectory, speed, and surrounding atmospheric dryness. Such a perfect alignment assembled only once during a decade of Dust Bowl conditions. It requires the right synoptic pattern at the right moment over the right source region, a combination that is uncommon even when the background conditions are favorable. However, this is where we must be cautious with the word rare, as our intuition about probability can be dangerously misleading. Black Sunday was, by definition, the most extreme event of its decade. It sat at the far end of the distribution of what was thought possible. Yet, its rarity did not make it unforeseeable. The conditions that made it possible were not absent until the moment it occurred. They had been present and accumulating for years. What was absent was only the specific trigger, the right cold front on the right day. The event itself was rare, but the underlying vulnerability that enabled it was not. That vulnerability was pervasive, persistent, documented, and ultimately ignored. The current data tells a familiar story. The distribution of possible outcomes across the southern plains has shifted, just as it did in the early 1930s, toward a higher probability of extreme events. The tail of the distribution, as statisticians call it, is getting fatter. This does not mean that another Black Sunday is imminent or inevitable. It means that the background conditions that elevate the probability of such an event are increasingly in place. The story of the Dust Bowl, then, is not merely a history lesson. It is a recurring cautionary tale about vulnerability, probability, and the profound consequences of ignoring the quiet accumulation of risk. A prolonged drought, lasting 6 consecutive years, has left the soil parched and vegetation sparse, bringing conditions perilously close to the point where dust can be mobilized on a massive scale. This vulnerability is compounded by over 1 million acres of land stripped of its protective cover by wildfires in just 3 months, on top of the pre-existing drought stress. Furthermore, the withdrawal of fragile, easily eroded lands from the Conservation Reserve Program for active farming adds another layer of risk. The powerful spring frontal systems, which provide the winds necessary for such events, are an annual certainty. The atmosphere operates on its own schedule, indifferent to our preparedness. The critical insight here is not to declare that a Black Sunday event will happen this spring. Such a claim would be irresponsible and is not supported by the evidence. Instead, a more honest assessment of risk acknowledges that the ingredients that made the original Black Sunday possible are more completely in place now than at any time in recent decades. This means the probability of a catastrophe of that magnitude is demonstrably higher than it was 10 or 20 years ago, and it continues to climb as these underlying conditions worsen. True risk assessment isn't about predicting a date. It's about understanding this shift in probabilities toward outcomes with devastating consequences. It's possible to imagine a scenario in the 1930s where an observer, armed with the available drought data, soil surveys, and vegetation maps, I could have looked at the conditions of April 1935 and issued a stark warning. With a basic grasp of synoptic meteorology, they might have concluded that the probability of an extreme event that spring was higher than it had been for years. The conditions were assembled. The trigger was merely a question of when, not if. The tragedy is that this person, or at least this potential for foresight, existed. The data was there, yet the warning was never issued with the urgency that the risk demanded. Then, on April 14th, 1935, the trigger was pulled. The enduring lesson from Black Sunday is not that such extreme events are beyond our ability to foresee. Rather, it is that anticipation requires us to clearly articulate what the data reveals before the event itself makes the point in a way that is both undeniable and irreversible. But there is another version of this story, one that lacks a single dramatic turning point. This is the slow-motion Dust Bowl scenario. In this future, there is no one Black Sunday, no specific date that historians will later identify as the beginning. There is no iconic photograph of a dark wall of dust bearing down on a farmhouse, no moment of collective shock that compels a nation to face what has been unfolding in plain sight. What exists instead is a sequence, a slow, grinding, almost imperceptible buildup of deteriorating conditions, mounting losses, and quiet departures. Over years, and then decades, the cumulative effect becomes indistinguishable from the catastrophe of the 1930s. Yet, it unfolds at a pace that never quite reaches the dramatic threshold needed to provoke a decisive political response. This scenario, more than a sudden cataclysm, is what keeps agricultural scientists and soil conservationists awake at night. The true danger of this gradual decline lies precisely in its subtlety. To understand this trajectory, consider how it might look from the inside, year by year. In 2026, dust events are severe, marked by haboob warnings, and air quality index readings reaching 1,400. The dust plumes are vast enough to be visible from satellites, and near-zero visibility leads to multi-vehicle pileups. While alarming to those paying attention, these events are not seen as unprecedented in a way that would trigger an emergency declaration. The drought monitor continues to show the same deep red and brown patches as the year before. Agricultural losses are substantial, but they fall within the range that federal crop insurance is designed to cover. The news cycle inevitably moves on. In 2027, the story continues, with agricultural losses climbing incrementally higher than in 2026. A few 100,000 more acres are withdrawn from the Conservation Reserve Program. Somewhere in Kansas, a few more miles of vital shelter belt are removed to accommodate a wider turning radius for farm equipment. Beneath the surface, the Ogallala Aquifer's water table in the Texas Panhandle drops another foot, perhaps two, a silent, invisible decline recorded only in the drilling logs of well contractors and the quarterly reports of groundwater districts that few people ever read. A region of eastern Colorado that slipped a full drought category in a single week in April 2026 never recovers. It stabilizes at its new, degraded level, only to fall further during the next bad month. Individually, none of these events are enough to cross the threshold for an emergency response. None generate a front-page story that holds the nation's attention. They fail to produce the kind of undeniable, photogenic disaster that shifts federal agencies from monitoring to action. Yet, taken together, year after year, they form a clear trajectory. The critical question then becomes whether anyone in a position to alter this course is watching with enough focus to grasp what they are seeing before it becomes irreversible. A trajectory, after all, is more telling than any single data point along its path. The agricultural economics driving this slow-motion scenario are not speculative. They follow a pattern documented in numerous historical analogues. It is a known sequence. As farming becomes increasingly marginal, with declining yields, rising input costs, and more expensive water, the land itself grows less productive under sustained drought. The first response from an individual farmer is often intensification. To compensate for lower yield per acre, you plant more acres. You run equipment harder and for longer hours. You draw down financial reserves to maintain cash flow and take on debt against land whose value has not yet caught up to its deteriorating condition. You might even plant crops on that marginal section of land you always knew was fragile, simply because you need the production and crop insurance will cover a potential failure. From the perspective of an individual farm manager facing real-time financial pressures, this response is entirely rational. In fact, most would likely make the same choices. The devastating paradox, however, is that what makes sense at the individual level is catastrophic for the system as a whole. Intensifying agriculture on degraded, drought-stressed soil does not stabilize the situation. It dramatically accelerates the degradation. That marginal piece of land, planted during a drought, does more than just fail to produce a crop. It loses the last of its residual vegetation, the cover that, while weakened by drought, had not been fully killed. It loses the soil structure that this minimal cover was maintaining. After just one or two failed seasons, that land becomes far more degraded than it was before it was ever planted, leaving it exposed and even more vulnerable. When a farm, under immense financial pressure, plants one extra marginal field to compensate for declining yields in its core, it risks creating a downward spiral. Within just a few years, what was once one degraded field can become two. This is the paradox where a rational economic choice can intensify ecological pressure, accelerating the system's overall decline. When this strategy of intensification eventually fails to stabilize the farm's economics, the next stage is abandonment. And it is here that the slow-motion scenario of the modern era diverges most profoundly from the crisis of the 1930s, not in its ultimate outcome, but in its mechanism and its pace. In the 1930s, the abandonment of a farm was a dramatic, visible event. Families loaded their possessions onto trucks and simply left, an exodus captured in stark photographs. The deserted farmsteads, empty towns, and clocks stopped in time became the visual signature of the disaster. A discrete and documented historical moment. The abandonment unfolding today, however, presents a very different picture. It looks like a bank in Amarillo, quietly foreclosing on an underwater farm loan in the fourth quarter of 2028. This might happen after 3 consecutive crop insurance payouts failed to keep the operation solvent, because the insurance covered the lost crops but not the cumulative degradation of the soil, which makes each successive harvest smaller than the last. It looks like a 6-8-year-old farmer in Deaf Smith County, whose children have built lives in Dallas and who can find no buyer for his land at any sensible price. He stops production not with a dramatic flourish, but with quiet exhaustion, because there is no reason left to continue and no energy to find one. It also looks like a 9-year-old who, after growing up on a high plains farm and earning an agricultural degree, returns home to take over. After running the numbers for 2 years, she makes the rational individual choice to pursue a different life, somewhere that isn't drying up, because she can see the trajectory is unsustainable. The water is disappearing, the soil is eroding, and the economics no longer work. Land in a state of drought is, fundamentally, exposed land. While the human mechanisms leading to this exposure are different from those of the 1930s, the physical result is tragically identical. We are left with vast areas of unprotected, denuded surface soil, sitting loose upon a flat, dry, and windy landscape with nothing to hold it in place. The wind, as an impartial force of nature, does not care whether the land was exposed because a family fled in a truck in 1936, or because a bank filed a foreclosure notice in 2028. It simply finds the vulnerable surface and begins its inexorable work. The response of the human population follows a similar pattern to the agricultural one, though it is stretched across a longer timeline and distributed over a larger geography, making it far more difficult to perceive as a single, unified phenomenon. For decades, the rural depopulation of the high plains has been underway, driven by agricultural consolidation, mechanization, and the broader demographic shift towards cities. What the slow-motion Dust Bowl scenario does is accelerate this existing trend, pushing the communities left behind past the threshold where they can maintain the infrastructure needed to remain functional. Across the Texas Panhandle, western Oklahoma, and southeastern Colorado, small towns have already seen their hospitals consolidated, their schools shrink from declining enrollment, and their Main Street businesses lost to regional hubs and online retail. What often remains is a skeletal network of essential services and a population that skews heavily elderly, the people who stayed because their roots were too deep, because they had nowhere else to go, or because they genuinely loved the very land they were watching die. When the agricultural economy deteriorates beyond the point where even marginal farming is viable, those remaining residents lose the very foundation that sustained even that skeletal community. The grain elevator closes because there is no grain to move. The equipment dealer shuts down because there are no farmers left to buy equipment. The last doctor leaves, unable to support a practice with so few patients. The town does not disappear overnight. Instead, year by year, it becomes a little less capable of sustaining human life with basic dignity. Measured across a decade, this quiet process is the modern equivalent of the Great Migration, the displacement of a population from a region that can no longer support them. It is driven by the same combination of drought, soil failure, and economic collapse that pushed the original migrants down Route 66 toward California. But this modern exodus does not look the same. It does not produce the same photographs, the same songs, or the same political shock. It produces instead a quiet statistic in a Census Bureau report, a line in a county development study, or a note in an agricultural survey about declining farm loan performance. The catastrophe is the same. The visibility is not. This scenario does not require a single dramatic event, like a Black Sunday, to trigger a disaster. It only requires that the current trajectory continue for another 10 or 15 years without a meaningful course correction. As documented across every dataset we have examined, the current trajectory is pointing in exactly that direction, without deviation. The soil is moving, the water is going, the farms are struggling, the towns are thinning, and the protective infrastructure is declining. Each of these processes is individually gradual, but taken together, they form a vector, pointing toward an outcome that the 1930s generation would recognize immediately, even if it arrives without the black sky and the wall of dust that made their version impossible to ignore. The mystery, then, is not what is happening. The mystery is why the response is so far behind the knowledge of what is coming. To understand that this is not some distant hypothetical, we only need to return to where we started. On March 15th, 2026, instruments in Lubbock, Texas, recorded an air quality index of 1,400. Federal weather forecasters in Amarillo issued haboob warnings for severe dust storms over agricultural land that is not a desert and was never supposed to become one. On a major highway, a multi-vehicle crash occurred in near-zero visibility, a direct result of blowing soil. And high above, NASA satellites captured dust plumes visible from orbit, originating from the very same geographic source region as the infamous storms of the 1930s. The evidence suggests the event is not on the horizon. It may already be here. In the midst of these unfolding events, the federal government continued its routine, issuing drought monitor updates and filing quarterly reports on agricultural losses. Yet, there was a conspicuous silence, a notable absence of any official press conference that dared to use the words Dust Bowl. It can be a powerful exercise to pause and take an inventory of a complex body of evidence, not as a mere summary, but to feel its cumulative weight. When viewed together, the individual pieces form a picture that becomes impossible to dismiss or rationalize away. Within the vast archives of a NOAA database, the Oceanic Niño Index was showing a specific pattern of ocean temperatures. It revealed a cool tropical Pacific alongside a record warm North Atlantic, the very configuration that researchers Cook, Miller, and Seeger had identified back in 2009 as the essential first ingredient for the conditions that created the original Dust Bowl. This was not a similar trend or a movement toward that state. It was a direct match. In parallel, the USDA's Conservation Reserve Program records offered another piece of the puzzle. Enrollment figures indicated there were approximately 11 million fewer protected acres than at the program's 2007 peak. This meant 11 million acres of fragile, erosion-prone land, once shielded by protective vegetation, were now exposed. The U.S. Drought Monitor further darkened the picture, showing 89% of Texas and 99% of Oklahoma mired in some form of drought. The duration of this episode had already surpassed the drought of the early 1930s that preceded the infamous Black Sunday, suggesting we were no longer just making a historical comparison, but entering the very territory those comparisons were meant to warn us against. The evidence continued to mount from other sources. Wildfire statistics for the first quarter of 2026 alone showed that more than 1,100,000 acres had burned across the southern plains. These fires stripped away the protective cover from land already pushed to the brink of failure by 6 years of drought. The air itself told a story of distress. In one major American city, air quality records registered an index value nearly 3 times the level the EPA classifies as hazardous. Pushing into a range the measurement scale was never even designed to accommodate. A subtle but significant shift was also occurring in the operational vocabulary of federal weather forecasters. Terminology, once borrowed from Saharan desert, meteorology, was now appearing in routine forecast products for the American plains. Each of these signals pointed toward a system under profound stress. What is perhaps most striking is that every single one of these data points exists within a publicly accessible federal database or a published government report. None of this information is hidden away. It requires no special clearance or insider access to uncover. The pieces are sitting in plain sight, waiting to be assembled into the coherent picture they collectively describe. And in the peer-reviewed scientific literature, published 16 years ago, a model since tested, validated, and cited hundreds of times laid out the precise mechanism producing all of these conditions. The recipe was documented, the ingredients named, the feedback loops quantified, and the thresholds identified. The researchers who authored that paper did so with the explicit goal of preventing a recurrence, believing that understanding the mechanism was the crucial first step. They effectively handed us the answer to a question we had not yet fully asked. And then, 16 years went by. We possess the understanding. We have the data. The monitoring systems are in place, providing a constant stream of information. Satellite imagery updated daily, drought maps revised weekly, ocean temperature indices calculated monthly, and air quality measurements refreshed hourly. The policy tools also exist. The Conservation Reserve Program is an operational reality. The shelter belt infrastructure, though diminished, still stands and could be expanded. Conservation easement programs are available, and the Natural Resources Conservation Service provides a network of technical assistance. These are not theoretical ideas, but functioning federal programs with staff, budgets, and established relationships in the farming communities they serve. While their funding has been declining when it should be increasing, the institutional architecture to scale them up is already there. The scaffolding has been built. What is missing is the decision to use it. As of April 2026, what we do not seem to have is a federal agency or a senior official willing to stand before the public and speak the sentence that the data has been composing for 6 years. A sentence that would simply state, the same conditions that caused the Dust Bowl are present today. These conditions were identified and described by peer-reviewed science 16 years ago. And the United States government must now respond at a scale that matches the reality of what is happening to American soil. That declaration has not been made. Its absence, in the face of all the evidence we have just inventoried, becomes one of the most significant facts in this entire story. It is a difficult but necessary exercise to consider what the generation that lived through the 1930s would make of our current situation. The comparison is a sobering one. The people who experienced the Dust Bowl firsthand did not have the Cook, Miller, and Seeger paper to guide them. They had no network of NOAA ocean buoys feeding real-time data into public indices. They could not turn to NASA's Earth Observatory satellites to see dust transport events from 200 miles above the atmosphere. With images posted online within 48 hours, they did not have a weekly national drought monitor map, color-coded by severity, to track the crisis. They possessed no general circulation climate models capable of isolating the precise impact of individual variables on vast atmospheric patterns. They had none of our modern tools. Their data was visceral and immediate. It was found in the people dying of dust pneumonia, in the children in rural Oklahoma hospitals whose lungs were filled with silica particles. It was in the farmers who stood on their porches, watching the topsoil of their entire livelihood blow east toward the Atlantic, calculating if they had enough money left for another month of food. Their data was a sky that turned black at noon on a Sunday in April. And yet, within months of that Sunday, they acted. They created the Soil Conservation Service. They funded and began planting 220 million trees across the Great Plains. They developed and deployed emergency conservation tillage practices on millions of acres and passed the legislation that would become the foundation for the conservation reserve concept. They moved with speed and at a scale commensurate with the problem, because the problem had made itself undeniable in the most tangible way possible. In 1935, those in positions of authority found the political courage to match the scale of their response to the scale of the crisis. Today, we have everything they did not. We have the satellites, the models, the real-time data, and the benefit of their hard-won experience. The knowledge is ours, waiting to be honored with action. We possess the early warning systems they operated without. We have the underlying mechanisms decoded before the worst consequences unfold, not after. We can track key variables in real time, not merely reconstruct them from memory and mortality records. We can also draw upon historical comparisons, not as living trauma, but as documented, analyzed, and peer-reviewed science. In every technical and informational sense, our position is superior, and yet, this advantage has produced a response that is alarmingly small. To date, we have generated essentially no action on the scale that the conditions demand. Instead, we have a cycle of monitoring and reporting, often accompanied by declining program budgets. We have perfected the documentation of a problem, but have not yet mobilized to address it. There is a term for this chasm between knowledge and action. In individual psychology, it is often called denial, but that word implies an active resistance, which may not capture the dynamics of large systems. In the world of institutions, this gap has more prosaic names perhaps more unsettling because they point to structural flaws. There is bureaucratic inertia, the tendency for vast organizations to maintain their course because changing direction requires energy that their incentive structures don't reward. There are misaligned incentives, a policy architecture that compensates farmers for losses rather than preventing them. It's a system that funds insurance payouts over conservation investment, making it economically rational to expose fragile land rather than protect it. We also see political risk aversion. The calculation by officials who understand the problem that saying "Dust Bowl allowed" carries political costs that silence does not, at least until silence becomes untenable. And there is fragmented accountability, where every agency sees its piece of the data, but no single body is tasked with assembling the full picture and acting on it. Crucially, none of these explanations require malicious actors. They do not need a conspiracy or a deliberate suppression of information. They are simply the normal operating characteristics of large government systems facing a diffuse, slow-moving risk. It is the institutional equivalent of delaying a doctor's visit for a symptom that develops gradually. If that same symptom appeared overnight, it would likely trigger immediate action. But because it has been building for years, there always seems to be a reason to wait one more quarter, one more budget cycle, one more growing season before escalating the response. This pattern of delay is a predictable, if dangerous, feature of how we process threats that do not arrive with sudden force. The conditions visible from orbit over the southern plains in the spring of 2026 are, however, not ambiguous. This point is vital because ambiguity is often used to justify institutional hesitation, and it does not apply here. The science describing what these conditions mean is not contested in any serious scientific forum. The peer-reviewed literature on the dust bell mechanism is not a fringe hypothesis. For 16 years, it has been tested, replicated, and built upon. The policy tools available to address the problem are also not experimental or unproven. They are the same mechanisms deployed after the original Dust Bowl, and they demonstrably worked. The only element of this story that remains a true mystery is not what is happening to the soil of the southern plains. That part is documented, measured, and understood. The mystery is what is happening to the response. The first Dust Bowl serves as a harrowing reminder of the stakes. It killed at least 7,000 Americans through dust, pneumonia, malnutrition, and the cascading health consequences of prolonged displacement and poverty. The disaster displaced 2.5 million people in what was the largest internal migration in American history to that point. It also destroyed 100 million acres of farmland, much of which has never fully recovered its original productivity. And it did all of this, even though the warning signs were visible for years before the worst arrived, visible to soil scientists, agricultural agents, and anyone who drove across the plains in 1933 or 1934 and looked at the ground. The catastrophe was not invisible, it was ignored. Those who ignored it did not act out of malice. They did so because their system was not structured to translate warnings into action before the cost of inaction became undeniable. We are in that position now, with better information and fewer excuses. This leaves us with a question whose answer is being written in real time. The story is shaped by decisions being made and not made in Washington. Its outcome hinges on USDA budget negotiations over CRP rental rates for vulnerable lands and on Farm Bill deliberations that will either restructure crop insurance incentives toward conservation or not. The narrative is also being written by individual farmers across the Texas Panhandle and southwestern Oklahoma, making planting decisions on land left desperately vulnerable by 6 years of drought. And it is being shaped by vast weather systems, assembling the atmospheric configuration that a peer-reviewed paper described 16 years ago as the trigger for the event we are trying not to name. This approaching storm is not a metaphor. The recipe for disaster is not theoretical. The silence surrounding it is not an accident. Somewhere, under a sky, our instruments can no longer fully measure. On soil that has been losing its structure and moisture for 6 consecutive years, the southern plains is waiting. It is waiting to find out what kind of story this will become. The kind where the warning was heeded, or the kind where it was not. The generation of the 1930s did not get to choose which story they were in. We still do, but that window of opportunity, much like the topsoil itself, does not stay open indefinitely.